Our solar system is a remarkable place. It's filled with a vibrant collection of celestial objects. At its heart lies the Sun, a star that provides light and warmth to its orbiting family. Around it dance 8 diverse planets, each with its own unique story. Rocky worlds like Earth and Mars huddle close to the Sun. Gas giants like Jupiter and Saturn, with their swirling clouds and numerous moons, roam farther out. But that's not all. Countless asteroids, icy comets and dwarf planets like Pluto add to the solar system's bustling cosmic dance. How did this intricate system, our very own cosmic neighborhood, come to be? Let's dive into the epic origin story of our solar system. Imagine a vast, cold and dark cloud of gas and dust drifting through space. This isn't just any cloud, it's a molecular cloud, a colossal and enigmatic structure that serves as the birthplace of stars and planetary systems. These clouds are often found in the spiral arms of galaxies, where they float silently, waiting for the right conditions to trigger their transformation. This is a molecular cloud, the birthplace of stars and planetary systems. Within these clouds, temperatures are incredibly low, often just a few degrees above absolute zero. The gas and dust are so dense that they block out visible light, making these regions appear as dark patches against the backdrop of the Milky Way. These clouds are immense, stretching for light years and containing enough material to form countless stars. The sheer scale of these clouds is mind-boggling, with some spanning hundreds of light years across. Within these vast expanses, regions of higher density can form, setting the stage for the birth of new stars. Our solar system's journey begins within one such cloud billions of years ago. In these dense regions, gravity starts to take over, pulling the gas and dust inward. Over time, these collapsing regions become the cradles of new stars and planetary systems. Disturbed perhaps by a nearby supernova explosion, this cloud began to collapse under its own gravity. The shockwave from the supernova could have triggered the collapse, compressing the gas and dust and initiating the process that would eventually lead to the formation of our Sun and its surrounding planets. As it contracted, the cloud started to spin faster and faster, like a figure skater pulling their arms in during a spin. This increase in rotational speed is due to the conservation of angular momentum, a fundamental principle of physics that governs the behavior of rotating bodies. This spinning motion flattened the cloud into a rotating disk of gas and dust, known as a protoplanetary disk with a dense bulge at its center. This central bulge would eventually ignite to become a star, while the surrounding disk would coalesce into planets, moons, and other celestial bodies, marking the birth of a new solar system. At the heart of this swirling disk, gravity continued to pull matter inward. The central bulge became denser and hotter, reaching unimaginable temperatures and pressures. Atoms, mostly hydrogen, were squeezed so tightly together that they began to fuse, releasing immense amounts of energy. This marked the birth of our Sun, a giant ball of plasma powered by nuclear fusion. The Sun's powerful gravity began to dominate the surrounding disk, shaping the destiny of the material orbiting it. Within the swirling protoplanetary disk, a remarkable transformation was taking place. Dust grains, remnants of ancient stars, collided and stuck together, forming larger and larger clumps. This process, known as accretion, is the key to planet formation. As these clumps grew, their gravity attracted more material, pulling in gas, ice, and dust from the surrounding disk. Over millions of years, these clumps transformed into planetesimals, the building blocks of planets. These planetesimals continued to collide and merge, gradually growing into the planets we know today. The type of planet that formed depended heavily on its distance from the young Sun. In the early solar system, the Sun was surrounded by a rotating disk of gas and dust, known as the protoplanetary disk. This disk was the birthplace of all the planets, and the conditions within it varied significantly with distance from the Sun. A crucial boundary known as the frost line emerged within the protoplanetary disk. This frost line, or snow line, was the point at which it was cold enough for volatile compounds to condense into solid ice grains. The location of the frost line played a pivotal role in determining the types of planets that would form. Inside the frost line, Where temperatures were higher, only rocky materials like iron and silicates could condense into solid particles. These materials were able to withstand the intense heat close to the sun, leading to the formation of small, dense, rocky bodies. Over time, these rocky bodies collided and merged, growing into the terrestrial planets we see today. This region gave rise to the inner rocky planets, Mercury, Venus, Earth, and Mars. These planets are characterized by their solid surfaces and relatively small sizes compared to the giant planets. Their proximity to the Sun means they have shorter orbital periods and higher surface temperatures. Beyond the frost line, the temperature was low enough for volatile compounds like water, methane, and ammonia to freeze into ices. These ices were abundant and provided the building blocks for a different type of planet. The cooler temperatures allowed these volatile compounds to remain solid, contributing to the formation of larger planetary cores. These ices provided abundant material for the formation of giant planets. The cores of these planets grew rapidly, reaching sizes large enough to attract and hold on to vast amounts of gas from the surrounding disk. This process led to the creation of the gas giants and ice giants that dominate the outer solar system. Jupiter and Saturn, the largest planets, accreted massive amounts of gas and ice, becoming the gas giants we know today. Their immense gravity allowed them to capture and retain thick atmospheres composed mainly of hydrogen and helium. These planets have no solid surface and are characterized by their extensive systems of moons and rings. Uranus and Neptune, while smaller, also form beyond the frost line, becoming ice giants with their own unique compositions. These planets have thick atmospheres rich in water, ammonia, and methane ices, giving them their distinctive blue hues. Their formation and evolution continue to be subjects of scientific research as they hold clues to the processes that shaped our solar system. Leftovers of creation, moons, asteroids, and comets. Not all the material in the protoplanetary disk ended up in planets. Smaller bodies, remnants of the planet-forming era, litter our solar system. Some planetesimals never accreted into planets and remain as asteroids, concentrated in the asteroid belt between Mars and Jupiter. Others, flung to the outer reaches of the solar system, became icy comets in the distant Kuiper belt and Oort cloud. Planets too played a role in shaping the solar system's debris. Some, like Earth and Jupiter, captured smaller objects in their gravitational pull, forming moons. These moons, often geologically active and harboring subsurface oceans, represent exciting destinations for future exploration. The early solar system was a chaotic and violent place. Around 4 billion years ago, a period known as the Late Heavy Bombardment pummeled the inner planets with a barrage of asteroids and comets. This bombardment, likely triggered by gravitational interactions between the giant planets, left its mark on the surfaces of the inner planets, including Earth. While destructive, these impacts may have also delivered water and organic molecules to early Earth, playing a role in the emergence of life. Our solar system is full of fascinating facts and ongoing mysteries. Did you know that the Sun accounts for over 99.8% of the total mass of the solar system? That's like having a basketball surrounded by a few grains of sand. Scientists are still debating the exact mechanisms that triggered the initial collapse of the molecular cloud that birthed our solar system. The search for exoplanets, planets orbiting other stars, has revealed a diversity of planetary systems, some vastly different from our own. This discovery has challenged our understanding of planet formation and sparked new questions about the potential for life beyond Earth. Our cosmic oasis, a universe to explore. The vastness of space has always beckoned humanity to look beyond our blue planet and wonder about the mysteries that lie beyond. From the earliest astronomers to modern-day scientists, the quest to understand our place in the cosmos has driven countless explorations and discoveries. The story of our solar system is a testament to the awe-inspiring power of gravity, time, and the intricate dance of cosmic matter. Gravity, the invisible force that binds us all, orchestrates the movements of celestial bodies, creating a harmonious ballet that has been unfolding for billions of years. From a humble cloud of gas and dust emerged a star, planets, moons, and a myriad of other celestial objects. This process, known as stellar formation, is a complex and beautiful phenomenon that continues to occur throughout the universe, giving birth to new stars and planetary systems, and countless smaller objects, each with its own unique history and character. Asteroids, comets, and dwarf planets all play a role in the grand tapestry of our solar system, each contributing to the dynamic environment we observe today. As we continue to explore our cosmic neighborhood, we gain a deeper appreciation for the delicate balance of conditions that allowed life to flourish on Earth. The presence of water, a stable climate, and the right chemical ingredients have all contributed to making our planet a haven for life. The universe is vast and full of wonders, with countless galaxies, stars, and planets waiting to be discovered. Each new discovery adds a piece to the puzzle, helping us understand the origins and evolution of the cosmos. And the story of our solar system is just one small chapter in its grand narrative. As we send spacecraft to explore distant worlds and peer deeper into the universe with powerful telescopes, we are constantly reminded of the boundless possibilities that lie ahead. So, keep looking up, keep asking questions, and let your curiosity guide you. The night sky is a treasure trove of secrets, waiting to be uncovered by those who dare to dream and explore, and never stop exploring the cosmos. The journey of discovery is endless, and each step we take brings us closer to understanding the true nature